So this is a demonstration of acquiring data from a nanoVNA vector network analyzer and then fitting a capacitor model to it. The capacitor model in question has parasitic inductance and resistance in addition to the core capacitance that we're trying to measure. And there are, of course, parasitics introduced by the test jig itself. The test jig consists of two header pins that are spaced 1/10 of an inch apart roughly, and the component, the chip capacitor itself, is wedged between these pins. There's a voltage divider involved which has an output impedance of around 60 ohms that's presented to the chip capacitor. And the estimation, the modeling that we're going to be doing, will be solving for the unknown, pretty kind of well-known loss through the jig, which is about 20 dB. That's designed in order to decrease the sensitivity of the jig to the input capacitance or input impedance of the vector network analyzer, which we don't exactly know. And it'll also be estimating the capacitance itself and the parasitic components. So here we go. This is going to be acquiring the data. It's acquiring it in equal frequency multiple increments. So this is close to logarithmic sampling in frequency. That gives us more data points at the low frequencies than we would have otherwise. Here's the fitting. You see it fit the levels at different times. And so our final results are gain of minus 17 dB instead of nominal 20. This is an input for the output impedance of the voltage divider, and then it's estimated our what is nominally 100 nanofarad capacitor to be 135, 136 nanofarads, and the parasitic resistance, which includes the actual test jig, to be 300 milliohms. This is comparable to the normal specification of about 200 milliohms that such a chip capacitor should have, and the parasitic inductance is 8.4 nanohenries. I think it's typical for the 805 package to have about 0.7 or 1 nanohenry in itself, but we've introduced quite a lot more in the wiring and the pins that are holding the chip capacitor itself. This 8 nanohenries is probably fairly typical of normal use though, because it's always in a circuit. So it's not a bad estimate. And you can see that the red line, which is the model that we've estimated, fits the blue line, or blue fuzz bar, which is what we got from the network analyzer, very closely. We get a little bit of divergence at the high end, where there may be a second effective capacitance in the chip, and we have a bit of noise at a little bit more than 10 kilohertz. These may be a switch mode power supply operating nearby or something like that, but it doesn't affect the model fit really much at all. Now the model fit is also done in terms of relative measurements, i.e. in an absolute difference in dB reading rather than an absolute difference in the measured value. Probably would be better to do it in terms of measured value, absolute deviation, rather than percentage deviation. But the fit worked quite well, and since we present it in terms of dB, this is a nice way to do the fit so that it looks good. The result is good either way, so we're probably fine. So we measured and modeled a particular real capacitor.